Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see we have a whole bunch of questions that are left over from last week. So let me take a look at a few of these. There's a question from Slayer here about what happens if you fall into the ocean from a great height. From what I've read, it's like hitting concrete. Can you explain the science behind this? Well, let's see. There are many parts of that. So one question is, if you drop something from the top of a tall building, from an airplane, something like that, how fast does it fall? So there are two pieces to this. One is, how fast would it fall if there wasn't any air? And another question, another part of that is, how fast does it fall given that there's air on Earth? So if you were to, let's start off with the question of how fast do things fall ignoring the fact that there's air. Assume you were dropping something on the moon where there's no atmosphere, where it's just a vacuum. How fast do things fall? Well, so the answer is that gravity the basic thing that happens is when you're dealing with something like a planet, a big object that has a lot of mass, it produces a gravitational field. It produces a pull of gravity that will pull any object that has mass towards it. And there's, at the surface of the Earth, there's this idea of the acceleration due to gravity, which is about 9.81 meters per second per second. So what does it mean, the acceleration due to gravity? So gravity is a force that is pulling objects that have mass towards the Earth, specifically towards the center of the Earth. And there's Newton's second law says force is equal to mass times acceleration. So you can turn that around and say acceleration is force over mass. But you can say that well, I got a little bit complicated here, but the force due to gravity is proportional to mass, and so those masses cancel out. And so the result is that when something is falling towards something like the Earth, what the effect of gravity is just to accelerate the motion of the object. So what does that mean? So something is traveling at a certain speed. Acceleration is the rate of change of that speed with time. And so what this is saying is that when something falls near the Earth, it is every second, it is going 9.8 meters per second faster than it was in the previous second. It's about 32 feet per second, I think. So in other words, what that means is at this second, the thing might be going, let's say, at 0 miles an hour. The next second, it's going at some number of miles an hour, some larger number of miles an hour. The next second, it's going at twice that number of miles an hour, and so on. So at every moment, it is increasing its speed. So that's what the effect of gravity does that. And that's true of any large object like the Earth. In a first approximation, things just fall at a certain constant acceleration towards the Earth. Same on the moon, same on other planets. The acceleration due to gravity is different on the Earth than it is on the moon because a couple of things contribute. The total mass of the Earth compared to the size of the Earth determines the acceleration due to gravity at the surface of the Earth. And so, for example, on the moon, the acceleration due to gravity is about 1/6 the acceleration due to gravity on the Earth. So the rate that things accelerate when they're falling on the moon is 1/6 the rate they accelerate when they're falling towards the Earth. Now, on the surface of the Earth, the acceleration due to gravity is more or less this constant 9.8 meters per second in most places on the Earth. There's a slight variation because, for example, for example, if there's a big mountain, if there's a question, if you drop something near the side of a mountain, the mountain itself has a bunch of mass, and so there will be a tendency for gravity. The mountain will produce gravity, and so the object, instead of falling sort of straight down towards the center of the Earth, it will be deflected to fall slightly towards the mountain because there's mass in the mountain that is like a miniature Earth in a sense that's pulling the thing towards it. So there is some variation of this 9.8 meters per second in different places on the surface of the Earth that has to do with things like that. and it isn't even always necessarily pointed precisely towards the center of the Earth. If you go away from the Earth, eventually, if you go far enough away from the Earth, there's no pull of gravity. There's no acceleration due to gravity from the Earth, because the Earth is the amount of gravitational force goes down like the 1 over the square of the distance between you and the object that's pulling on you. And so eventually, when you get far enough away from the Earth has no effect. Just like when on the surface of the Earth here, if we ask, how much effect does the gravity of the planet Mars have on us? The answer is almost none. So that 9.8 meters per second, as you go into space, for example, that number will gradually decrease, so that the amount of acceleration due to gravity will decrease as you move further away from the Earth. Okay, so first point is, if you drop something towards the moon, it will simply accelerate as a result of the gravity of the moon. And in a first approximation, if you drop something if you're really, really a long way away from the moon, really like, the distance away that Mars is from the moon, then nothing's going to fall towards the moon. But if you're reasonably close to the moon, things will fall towards the moon. They'll fall initially at an acceleration that's a little bit lower than the acceleration on the surface of the moon, but pretty soon they'll be falling at the acceleration that's close to the acceleration on the surface of the moon. And the moon, which doesn't have any atmosphere, they'll just accelerate according to that rule, and they'll just go faster and faster and faster. And if the and so it's a little tricky. You can work out, you can kind of reverse the problem, and you could say, if you were shooting a rocket from the Earth, how fast does the rocket have to go in order to fully escape the Earth's gravity, the escape velocity of the Earth? That's 25,000 miles an hour for the Earth. And that actually tells you, if you were to drop something from very far away from the Earth and let it accelerate due to the acceleration due to gravity as it approaches the Earth, when it gets towards the surface of the Earth, it will be accelerating at 9.8 meters per second. When it's further away from the Earth, it will be accelerating less rapidly. If you do the calculus thing of integrating that acceleration, you can work out what the velocity that the thing would have when it gets to the surface of the Earth, and the answer is 25,000 miles per hour. So in other words, if you dropped something from far enough away from the Earth, and the Earth didn't have an atmosphere, and you let the thing accelerate towards the surface of the Earth, it will be going at 25,000 miles an hour when it hits the Earth. And that's, you can work that out for other things. For the sun, for example, it's around 100,000 miles an hour, and so on. So so assuming there was no atmosphere, that's how fast things will be going. That's really fast. To give you a sense of scale, the speed of sound is around 600, 700 miles an hour, depending on exactly where in the atmosphere you are and so on. So that's many times the speed of sound. The speed of, what are some fast things? The fastest, the typical, commercial airplanes fly at about maybe 0.8 times the 80% of the speed of sound. Something like, a bullet shot out goes at maybe twice the speed of sound. So 25,000 miles an hour is fully, what is it? It's about, well, that would be Mach. That's the sort of, that's unit of speed of sound. That's like, well, actually, that would be like Mach 30 or Mach 40 or something. That's extremely fast in terms of just sort of things, and most things, if you were to crash into the Earth at that speed, not much would be left. Most things would vaporize at that speed. Okay, so I'll tell you a little bit of a story here. A couple of years ago, a friend of mine who has a slightly peculiar activity of trying to get sort of objects that are kind of representative of our civilization deposited around the solar system, managed to make an arrangement with an Israeli group that was sending a spacecraft to the moon, a thing called the Bereshit lander. This spacecraft, he got this little quartz disc that he got placed on the spacecraft. It has a bunch of micro dot versions of lots of interesting works of human literature and so on, including even some things I've written. And it's kind of a cool thing to sort of deposit that on the moon as a backup of the backup of the backup of where you can put kind of the works of our civilization. Not clear who's ever going to look at it, but it's a fun concept, at least, to have that thing be on the moon. Okay, so the bad news was this lander, as it approached the moon, something went wrong. And the lander crashed into the moon at, I think, about 2,000 miles an hour. I think it crashed into the moon at close to the escape velocity of the moon. So that would be, let's see, can I do my math properly here? Well, that would be a little bit faster than that. So I think it was around 2,000 miles an hour that it crashed into the surface of the moon. And so the question was, when an object crashes into the surface of the moon at 2,000 miles an hour, what happens? And another friend of mine who happened to have a rocket company for a number of years, I asked them about this because they'd had rockets that unfortunately failed. And they described the process as, imagine you take the main gun on a battleship, which has a great big shell that it fires, and you fire that gun into a piece of concrete. That was his analogy for what would happen if you had this spacecraft hit the moon at 2,000 miles an hour. And it's like there's not much left. But it turned out that things were luckier than that, because it turned out this spacecraft, it had failed to fire its rocket engine at the right time. And so it had failed to basically come out of orbit properly. So when you're in orbit around something like the moon, you're going around rapidly around, sort of in parallel to the surface of the moon. You're sort of you're in orbit, so you're going around the moon. But then if you want to sort of land on the moon, what you have to do is kind of stop the speed that you're going around in the orbit and just go to be kind of straight down towards the moon, sort of falling towards the moon and hopefully firing your rocket engines to stop you before you hit the surface of the moon at high speed, as we've been just describing. So this particular spacecraft failed to deorbit properly. And so it was still going sort of in sort of parallel to the surface of the moon, as well as falling towards the moon. And so what happened is it actually hit the surface of the moon, not straight down, sort of splat, but it hit it at an angle. And in fact, it was at like a 5% incline. So it was mostly going, most of that 2,000 miles an hour was going parallel to the surface of the moon. It was kind of sliding relative to the surface of the moon, not going splat straight down into the moon. So the question was then, what happens to a spacecraft that hits the moon at that kind of angle as it's, and the answer, I found a person who's sort of a world expert on cratering, who said, well, actually, the thing will not just go splat into the surface of the moon. Instead, it will make a little crater where it first impacts, and then it will bounce and slide along the surface of the moon. So it will kind of be a thing where you can work out, how long will it take something that's just, sliding along a, something, I don't know, a beach or something, sliding along the sand. How long will it take a thing that's started at 100 miles an hour to stop when it's sliding along the sand? You can kind of work that out. And I had, in fact, done a little calculation of that for this spacecraft on the moon, assuming that it didn't run into a big boulder and just sort of crash into the boulder. And I had worked out that it would be several miles that it would slide on the surface of the moon, much because it was going very fast. And also there's less gravity on the moon to make the friction higher. So I was kind of surprised by that result and didn't really believe it. But the cratering expert told me that's actually correct, that the thing would actually slide for like a mile or something before coming to rest. So, okay, so then the question is, what actually happened to this thing? And the Lunar Reconnaissance Orbiter, which takes high resolution photographs of the moon, had gone over the landing site. And in fact, you could compare the picture before the spacecraft impacted the moon and the picture after, and you could see that, yes, there was, in fact, very satisfyingly, there was this big sort of streak outwards that from the actual expected landing site, there was a kind of streak going in a certain direction. And we worked out, based on the last picture the spacecraft had taken before it crashed, we could tell from that picture, it had certain craters in the picture, so we could tell where that picture was taken, and then we could figure out by sort of joining the vector of from where that picture was taken to the crash site, we could tell what direction it was going. We could tell the ray that one could see on the surface of the moon from the Lunar Reconnaissance Orbiter was in fact going in the correct direction for the sliding of the spacecraft. So it was undoubtedly doing exactly what the cratering expert had said, and it was the spacecraft having sort of bounced out of its initial crater and then sliding over the surface of the moon, and quite possibly my friend's quartz disk is still intact on the surface of the moon. I will say that my friend also sent some other rather more questionable kinds of things to the surface of the moon, including some things called tardigrades, which are a type of otherwise known as water bears. They're a type of critter that survives very well in very adverse circumstances, including vacuums and very cold and so on. And it wasn't the smartest idea to send some kind of living organism to the surface of the moon, probably. It's something where, you know, if people come back in a long time and they find, oh, wow, there's these critters living on the surface of the moon. Well, actually, they were sent there in the year 2020 by this person who didn't use the best possible judgment about what to put on a spacecraft going to the moon. But in any case, that's sort of a different topic. Okay, so that's the story of what happens when things are dropped without an atmosphere, when things just fall according to the laws of gravity and so on. They end up, if they're dropped from a very great height, they'll end up crashing into the surface of the planet or moon or whatever at the escape velocity of that body, which is, in the case of the Earth, 25,000 miles per hour. Okay, but there's a big footnote to that whole thing, which is, well, the Earth actually does have an atmosphere. There is air, and the air will tend to slow things down. So one knows perfectly well if one throws something through the air, it will, or one has a car going through the air or an airplane going through the air, there is air resistance. What is that? Well, what's happening is, as the thing, whatever it is, the plane or the thing you dropped, whatever, is moving through the air, it has to push the air out of the way in order to get through that particular place. And so what has to happen is that right at the surface of the object, there is the molecules of air are hitting the object and they're bouncing off the surface, and they're having to be, and they'll have to flow around the surface. So you can think about it at two levels. One is what happens to the molecules. The other is, if you think about sort of the air currents around the object, there has to be this kind of flow of air around the object. It's very much the same thing happens in water. You can see if you kind of run your hand through through water, you can see that there'll be this kind of there'll be this wake that's left by your hand behind your hand in the water, and that's kind of the you had to push water out of the way in order to move your hand forward, and that as the water comes back behind your hand, that will make the structure of this wake. Okay, so the question is, how much resistance to motion is there associated with a fluid like water or like air? And it turns out there are different regimes of flow. So at low speeds, there's what's called laminar flow, and at higher speeds, there's so-called turbulent flow. So what is laminar flow? So what's happening is, as you move your finger through the water, one possibility is that the water is just sort of separated by your finger, and it smoothly kind of slides around your finger and then comes back and recombines behind your finger. Laminar flow is this kind of smooth kind of thing where you have these kind of layers. That's where the word laminar comes from, these layers of fluid around where your finger is going, and that it's kind of a smooth sliding through the fluid. Okay, so there's a fact about that, which is in laminar flow, the resistance to flow is proportional to the speed of your finger. So it's proportional to velocity. The formulas for the more or less, there's a few detailed caveats to this, but more or less, the resistance of motion to motion is proportional to the speed. Okay, so the faster you're going, the more that the water is going to push back and stop you going that fast. Okay, as things go faster, what you'll see is you look at, behind your finger, you go sufficiently slowly, the water will sort of slide around your finger and recombine behind. As you go a little bit faster, you'll start seeing little eddies produced behind your finger. You'll start seeing these little vortices where the water is going around in a circle. And you'll see behind your finger, there'll be eddies that break off, first from the top, then from the bottom around your finger. There'll be this kind of what's called a vortex street of pairs of eddies that go off one, the top one, then the bottom one, top one, etc. It makes this kind of street of eddies behind your finger. And that happens as you go slightly faster. As you go even faster, what will happen is that street of eddies will start becoming irregular. The eddies will no longer form this kind of nice kind of lamppost pattern or something. They'll instead have a more complicated structure. And as you make your finger go even faster, the flow will no longer be regular like that. It will start to look much more random, and eventually it'll just look completely random. But there'll be this wake, and it'll be a so-called turbulent wake, where you have sort of random motion of the fluid behind you. So the mathematics of laminar flow is reasonably well understood. It was understood 100 years ago. The mathematics of turbulent flow is still not well understood. There's many aspects of it that are not known, but some aspects are at least empirically known. So, for example, in turbulent flow, the typical resistance to motion is not like the velocity, but it's like the velocity squared. Okay, so that's the when you drop something and there's turbulent flow around the thing, then the resistance to motion will be like the square of the velocity. The faster the thing is going, the more resistance there'll be, and then it'll go up like the square of the velocity. Now, it also matters, in addition to what the dependence on velocity is, there's also what the total amount of force associated with resistance to motion is, and that depends on the shape of the object. And so that's when the whole issue of streamlining and so on comes in. So if you have an object and it's a great big sail, it's going to be the amount of force associated with going through the air is going to be much larger. If it's a parachute, for example, the whole point of a parachute is to have a very big area that is set up so that there's the maximum resistance to motion, so that the parachute slows you down as much as possible. If you want something that's going to go really fast, you want something which is streamlined, which is has an aerodynamic shape. It has some kind of very pointy shape that's kind of separating the air in the best possible way and not having a lot of resistance to motion. So there's a thing called the drag coefficient, which characterizes kind of the result of whatever shape you made. So things that have like a sphere will have a certain drag coefficient. I think it's around 0.15 usually for typical 10 miles an hour or something type motion. Different kinds of shapes will have different drag coefficients, and they can vary a lot depending on whether it's a very pointy aerodynamic shape or a very parachute-like, sail-like shape that just has lots of area and is just trying to kind of stop the air. I should also have said that another thing that matters to the air resistance is what the area that the total area of thing that the air is hitting. So in any case, the bottom line on all of this is there's all kinds of resistance to motion associated with having to move through the air. At low speeds, it's this laminar flow idea. At higher speeds, it's turbulent flow. At lower speeds, it's proportional just linearly to the speed. At higher speeds, it's proportional to the square of the speed. So lots of resistance to motion. And that resistance to motion produces the following effect. So the acceleration due to gravity just makes you go faster, faster, faster. But if you work out the kind of calculus equations with this resistance to motion in it, it turns out that what happens is you eventually reach a so-called terminal velocity. Eventually, the gravity is trying to make you go faster, but this air resistance is trying to make you go slower. And the result is that you reach a constant velocity and you don't go any faster than that. And depending on the shape of the object, the terminal velocity will be different. So, for example, a typical person falling through the air, the terminal velocity is around 100 miles an hour. And that's so even though if there wasn't any air, they would hit the ground at 25,000 miles an hour, because there's air and because they're the shape they are, roughly sort of I don't know what shape we are, just sort of roughly a sphere in a first approximation, the result of that is the sort of trade-off between resistance of motion due to the air, acceleration due to gravity. It ends up with a terminal velocity of about 100 miles an hour. Now, different things will have completely different terminal velocities. Like you drop a feather, it has a completely different terminal velocity. That because it has high resistance to motion, because of the shape and so on. So its terminal velocity will be a tiny fraction of a mile per hour. So the question of the rate at which things fall depends on their shape. It depends on it also depends on their mass in the air, and depends on their size and so on. So there can be great variation. I mean, things that are very aerodynamic. Things, you have your average, missile or something that's been intended to fall rapidly through the air. It will fall at a much higher speed and so on. It might be at Mach, maybe 5 times the speed of sound or something like that, which is on the order of a few thousand miles an hour, as compared to sort of the falling person, which might be 100 miles an hour. So then I think our question had asked, what happens if you hit water at that speed? Well, it's the same kind of story. How to think about this? If you just dive into water, I should explain, when people do diving and so on, they try and make themselves as aerodynamic or hydrodynamic as possible, so they will just sort of slice their way into the water rather than going splat on the surface of the water. And this is the same phenomenon as asking what is the it's the same kind of idea as this question of terminal velocity in the air. If you make yourself more aerodynamic, your terminal velocity will increase. And so what's happening in the case of the water is, in a sense, if you hit the water, you will be, depending on your shape, there will be a certain essentially terminal velocity in water. If that terminal velocity in water is close to 0, then you will be going from whatever speed you were going at, and then you kind of go splat on the surface of the water and you're decelerating very rapidly. And that's bad news, so to speak. But if you can make yourself very hydrodynamic, very kind of slicing into the water, then your terminal velocity in water will be higher. And so the difference between whatever speed you were going at, which would be probably the terminal velocity in air, and your terminal velocity in water will be less great. And so you'll have less deceleration as you go into the water. So, the problem for us humans is that we don't do very well when we're rapidly accelerated or decelerated. So, for example, the acceleration due to gravity, 9.8 meters per second, we can ask the question, if we were to be, in a plane that's, put its engines on full throttle, or a car that is being accelerated as quickly as possible, what is the acceleration that is associated with that? So, for example, in a car, you can go 0 to 60 miles an hour in some number of seconds, and that will determine the acceleration for the car. And so, I'm not sure. I think let's imagine that the car was accelerating at 9.8 meters per second. That means that that there will be an effective. It's as if there's a force of gravity that's pulling you back into your seat, so to speak, at the same sort of with the same acceleration as the Earth's gravity is pulling you down. So effectively, then it's as if the direction of gravity moved from being down towards the Earth to being more back towards the back of the car, so to speak. And so I don't know. I think what is the accelerations of? I think the fastest, like with planes and things, like small corporate planes and things, I think maybe you can get to 2 Gs of acceleration or something like that from just, put the engines on full throttle and go from nothing to, zipping down the runway at 100 miles an hour or something. And maybe race cars, I don't know how fast they can accelerate. Another place where you see acceleration like that is if you're in a roller coaster, for example. The roller coaster is going, up to the top of a big sort of roller coaster hill and then running down to the bottom, and it runs down. It's accelerating more or less at the acceleration due to gravity of the Earth, and then at the bottom you're being turned around so that you're then going back up again, and there's acceleration associated with the change of your speed and the change of the direction of your motion associated with that. But the same is true when you're so a good way to sort of simulate acceleration is you just spin something around, and there will be acceleration because you're changing the direction of the velocity. You're changing the direction the thing is going, and that in order to change that direction, that change of direction corresponds to acceleration. And so you can have these centrifuges where you're the people in the early days of the space program, there was a lot of testing of what would it be like for people to be at certain different accelerations. And they had these big centrifuges, and people would kind of sit in a little capsule at the end of the centrifuge. They whirl the centrifuge around at different rates, and that would give you different different accelerations in that capsule. So I think people do. The question is, what happens at very high accelerations to us humans? And by 5Gs, that's high acceleration. 5 times acceleration due to gravity, that's high acceleration, and all sorts of terrible things happen. I mean, it's like, the blood drains from one part of you into other parts of you. This is an issue for people in military planes, where the planes can do maneuvers that have high acceleration. You have to keep the pilot from blacking out because all the blood's gone from their brain, and they can no longer get oxygen to their brain, and so on. And so there's a lot of sort of stuff to do with having a pressure suit that sort of forces blood to different parts of the body and things like this. And it tends to be the case that there's a lot of sort of detail of that. But one question is, in the case where if you're sort of in some car crash, where the car is going at 60 miles an hour, and you are about, and you just the thing rams into a brick wall, and how much acceleration is there? The answer is it can be 10 to 20 Gs of acceleration, and that's really bad for us humans. The way that things work, like with cars, typically modern cars have there's this sort of crumple zone at the front of the car, where if the thing's going to run into something, it will tend to be the case that the front of the car will kind of crumple, which will reduce so in other words, the main part of the car is going at 60 miles an hour, and if it was just going from 60 miles an hour to nothing, then that would be a very high acceleration. But because there's a part of the front of the car that will sort of gradually crumple, not very gradually, it takes thousandths of a second, as the thing crashes into something, then that will make the acceleration of the humans, for example, in the car be less than it would otherwise have been, because it sort of more slowly comes to rest than it would have done if it had just gone straight into the brick wall. But bad things happen. All sorts of bad things happen to us. I think that one of the really bad things is that I think one of the typical things is there are arteries connected to our hearts, and they don't do very well in high acceleration. So that's one of the very bad things that happens. The good news about lots of modern cars, for example, is that they have a hard time being crashed straight into a brick wall, because they tend to have this kind of emergency braking idea, which is usually based on well, I guess it's based on, I guess nowadays, either radar or visual cues, that the thing will even if you it will tend to automatically brake and prevent that from happening. I think the maximum rate when you slam your foot on the brake of a car, I'm not sure what the maximum acceleration is. I'm guessing a couple of Gs, where a G is the acceleration due to gravity on the surface of the Earth. So, okay, long answer to your question about what happens if you fall from a great height. Let's see. Oh boy, we've got some other physics ones here. Let's see. There's a question from Igor. Can I explain the origin of the white trails from jets at high altitude? So these are the so-called contrails, and what's happening is that it's kind of like miniature clouds. What is a cloud? A cloud is water vapor that is almost condensing into liquid water. If it were to fully condense into liquid water, it's like steam that is almost condensing into liquid water. If it fully condensed into liquid water, it would be rain, and the rain would fall from out of the cloud. But what's happening in a typical cloud is that you're getting sort of the beginnings of condensation into water, but into liquid water, but it isn't quite there. In particular, what happens is, it's sort of a funny thing. So normally you think of water, you've got a big pile of liquid water, you heat it up, eventually it will boil and you'll get steam. Okay, as you change the pressure of the air, different things can happen. So you can, at different pressures, it'll be a different temperature at which the water turns into steam. Okay, there is also a certain pressure at which you reach this, a little bit complicated how all of this is put together, but you reach this thing called the critical point. And at the critical point, the liquid water is so kind of rarefied, it's not very dense. And the vapor is quite dense. And in a sense, you can't tell the difference between the vapor and the liquid water. And at that critical point, one of the things that happens is you essentially, it's like the water vapor has little droplets of water in it, and the full water is like a big giant droplet of water. But what happens at the critical point is that there essentially are droplets at all sizes. And it's typical of a phenomenon in statistical physics to do with critical phenomena. But basically you have, essentially it's like droplets of all sizes. And one of the consequences of that is that the reason clouds are white is because they have droplets of sort of all the different sizes that will be necessary to do things to light of all different frequencies. Light, depending on the frequency, it has a characteristic wavelength. Well, this is suffice it to say that the way that clouds are white because they have droplets of all sizes, and that means that the light of all frequencies, whether it's yellow or red or blue or whatever, is always essentially reflected from the cloud. And so it ends up looking white. But what happens in contrails is that as the plane goes through the air, it disturbs the air, and it produces it essentially is causing condensation. It's cloud-like condensation, I think at this critical point, to form behind the plane. And what typically happens is, the big place where that happens is the wingtip vortices of the plane. So what happens is that a plane, if you look at the motion of air around a plane, one of the big effects is that there's a kind of swirling of air at the end of the wings of the plane. There are these vortices that form behind the plane, and those, I think, are the places where the primary places where these contrails form, is associated with the fact that the air sort of wants to condense into water, but it doesn't know where it should start. It doesn't know where the first droplets should form. And when the plane comes through and perturbs the air, it provides this kind of, it makes the air sufficiently non-uniform that the air changes its density a little bit. And that's the place where this condensation starts to form. And people, there are questions that I don't know the answer to that have to do with exactly what determines when contrails will form. And I think it's very random. People are not very sure. A given plane, sometimes it'll make giant contrails and sometimes it won't. You might think, does it matter what the shape of the wings is? What does it matter to how the contrails are formed? Actually, the wingtip vortices, the general circulation of the air around a plane, there's a certain amount of circulation that is necessary for the plane to get the lift to stay flying. So that is very much not something you can really change by just changing the shape of the wings. Planes end up having these little winglets at the end where the wing is mostly flat, but it kind of goes up at the end. And you might think that would affect these wingtip vortices. I don't think it does. Those are mostly to do with flow near the speed of sound. Those affect the details of the flow around the wings near the speed of sound. I don't think affect the overall circulation. I don't think affect the rate of contrail formation. So there's a question here. Okay, we're from Brian. If we rub mineral oil on us, will we move faster in water? Ah, yes, an interesting question. So there was a big effort for submarines. Submarines, you want them to go faster. Can you do something that will make a submarine slide through the water more quickly? I think one thing that has been done is if you boil the water right around the submarine, if you can make the water really hot right around the submarine, it will slide much more easily through the water than if the water is just, in a sense, right at the surface of the submarine, kind of sticking to the submarine. There's a whole technology of trying to coat things in something that will make the water kind of stick to the surface much less. So what happens right at the surface? So at the surface of the submarine, you've got the water that the submarine is in, and what's actually happening? Well, molecules are hitting the surface of the submarine. The submarine is going at a certain speed. The question is, put in a sort of physics terms, does some of the momentum of the submarine get transferred to these water molecules? In other words, when a water molecule hits the submarine, does it end up bouncing back in such a way that it is it kind of knows that it hit something? In other words, okay, if you've got a ball and you're shooting it at something that's completely stationary, the ball will bounce back at the same angle that it hits the thing at. So it'll just bounce off. It'll hit at a certain angle. It'll bounce off at the same angle. If the thing that it hits is moving, then that may not be the case, because some of what may happen is that some of the motion of the thing that the ball hit gets transferred to the ball. And when that happens, the result of that, if you had it be the ball turn into lots of molecules, the result of that is that some of the sort of forward motion of the thing gets transferred to forward motion of the material around it, of the water, let's say, around it. And that means that it is essentially there's more force needed, because not only are you trying to move the submarine through the water, you're also trying to move this whole layer of water that is near the submarine that is trying to be pulled at the same speed as the submarine. So in effect, you're trying to push through the water, not just the submarine, but this much bigger mass of water that is trying to move at the same rate as the submarine. So if you could make the submarine be kind of just slide through the water, then it would work much better, because then you wouldn't have to move this big mass of water, because it would just be, there's the submarine moving, but it doesn't move this mass of water. In a sense, what you're doing is to sort of lubricate the motion of the submarine. So when if you have something like, you have two solid surfaces and they're kind of grinding against each other, and one is sort of trying to move the other one, or let's say you have something and it's some kind of axle, and it's got some kind of casing around the axle. The axle is turning around, but it's got a casing around it that's keeping the axle in place. But the casing around it is producing friction that's trying to stop the axle from moving around. In a sense, what the axle wants to do is to try and turn its casing around with it. But if you keep the casing fixed, there'll just be friction between the axle and the casing. How do you make that friction less? Well, you put a lubricant like oil in, and what that lubricant is doing is it's kind of making it be the case that it no longer has to be true that this solid object there is is directly touching this casing. Instead, it's got this layer of liquid in between, and one side of the liquid, the side of the liquid that's right close to the axle that's turning around, will turn around along with the axle. But then then there's the liquid. There isn't the liquid that's close to the casing will be stationary, and depending on the characteristics of the liquid, you can make it be the case that the thing will just allow things to sort of slide more easily. And you can do the same thing with submarine moving through water. It's the same idea, except that instead of trying to prevent sort of friction between two solid objects, you're preventing friction between one solid object and one liquid. And so many experiments have been done on many kinds of molecules that you could coat submarines in and so on, that would make the resistance be smaller. And people sometimes claim remarkable results about that that depend on particular properties of molecules. And I don't know all the details of that. And many of those details are probably secret because people don't want people to know, just how fast military submarines move and so on. Okay, let's see. Boy, more of these. So there's a question here from Wardrobe. How long will we survive if the Earth left the sun's orbit going away from the sun? Well, that's a good question. So the good news is it's tough to see how that would happen. I mean, it could happen. If an asteroid collided with the Earth, it might throw the Earth off, out of its orbit, and it might start sort of careening away from the sun. But okay, so what would happen if the Earth, for some reason, moved its orbit further away from the sun? Obviously, we would stop getting solar radiation. We'd stop getting the heat and light from the sun, and the Earth would gradually cool down. And the question is, one question would be, at what rate would the Earth cool down? So one thing that's worth knowing is the center of the Earth has still not cooled down in 4.6 billion years since the Earth was formed. The center of the Earth still has heat that is left over from when the Earth was formed. And in fact, one of the things that's surprising, so the basic story would be, if you want to stay warm, go underground. And one of the things that's sort of surprising is, if you look between summer and winter and things like that, the air is changing temperature a lot in most places between summer and winter. But if you dig down in the soil, if you dig down in the ground, you don't have to go very deep before there's really no change in temperature throughout the year. And there's a certain average temperature, I think it's about 50 degrees Fahrenheit, typically in many places on the Earth. That is, if you dig down, I'm not quite sure how far it is, it's only a few feet. You dig down that distance in, for example, soil, it is the case that the rate at which heat is transmitted through the soil is slow enough that throughout the course of a whole year, there's almost no temperature variation in the temperature of the soil at that depth. And as I say, that's a sufficiently extreme effect that when it comes to temperature sort of escaping from the center of the Earth, in billions of years, that hasn't happened. I mean, there are other sources of heat in the Earth, about half the heat in the center of the Earth. The center of the Earth is molten. Below the crust, that's maybe 50 miles-ish down around on the surface of the Earth. If you go down below that, you get to the mantle of the Earth, and the mantle of the Earth is liquid. It also has a core in the middle that's probably solid. But most of the Earth's interior is liquid, and that the heat that keeps that liquid, some fraction, maybe half of it, is left over from when the Earth was formed 4.6 billion years ago, and half of it is due to the decay of radioactive elements that release energy and release heat. But that gives you a sense of the fact that you can stay pretty warm by just digging down and using rock to keep you insulated, so to speak. So I kind of think that you can do that. If it's a question of, do you get to use, how do you get energy? Well, you can do the same. Solar energy is less and less of a thing as we get further and further away from the sun. I mean, it's worth realizing, even on the surface of the Earth, it's a big deal what latitude you're at. If you're close to the North Pole, then there will be times of year where, well, the times of year when it's just dark. Half the year it's dark above the Arctic Circle. And so clearly, if you want solar energy during that period of time, you're out of luck. But for example, it's a calculation when people have, for example, high altitude drones that are going to get their power from photovoltaics, from solar cells, effectively. It really matters what latitude they're flying at, how far north they are, because the effective amount of solar radiation depends on the angle at which the sun, at which you're kind of the angle of the surface of the Earth relative to the sun. And so typically, many of those systems, it'll be like, it only works up to the northernmost part of the US. It won't work in Canada because there just isn't enough solar radiation at that angle, and so on. Or it'll work much better in the Caribbean than it does in in Minnesota or something. So let's see. For some reason, I'm reminded there's a Chinese science fiction movie that came out fairly recently that's about exactly this point of if the Earth moved away from the sun, what happens? And I think that's a story of then you live underground for a long period of time. How well that really works for us humans, I don't know, but that's a different kind of question. All right, let's see. Let's see, there's a question here from Kay about, could everything that gets sucked into all the black holes everywhere in the universe go to the same place? Okay, the bad news is it doesn't go anywhere, because a black hole is this region of space where which has an event horizon around it, which means things can go into it but can't get out from it. Well, the type of event horizon that black holes have has that characteristic. There are other event horizons where things can't go in either direction. But with a black hole event horizon, things can go in but can't come out. And the reason that happens is there's sufficiently much gravity associated with this black hole that the escape velocity is larger than the speed of light. So even if you were a photon going at the speed of light, you can't go fast enough to escape the gravity associated with this black hole. Well, so what happens in one of these black holes? Black holes arise from, in practice, the ones we have observed come from the collapse of massive stars that eventually no longer can get sort of kept at sort of star size by all this heat that's being produced by nuclear reactions in the star. They collapse, and they collapse down to the point where they're sort of crushed by the gravity of the object, and they get crushed into this very tiny region that may be a kilometer across or something, but has all the mass of the star in it. And that is sufficiently much, there's sufficiently high gravity there that you have this phenomenon of forming an event horizon, having it be the case that the escape velocity is larger than the speed of light. So the question is, what happens inside that region that is that where nothing can kind of get out? And the answer is, the mathematics of what happens in such a region, the mathematics of what can happen in Einstein's equations for gravity and for the structure of space-time, that's comparatively easy to work out. What are some possible things that could happen that have an event horizon and have the equivalent of mass inside? What actually happens with a collapsed star inside can be more complicated. But what happens in the kind of theory of these things is you form a singularity in space-time. So normally what happens is, oh boy, this is getting I'm backing into some kind of complicated things. So roughly what happens, okay, so think about how do we understand the structure of space? One way we can do it is we shoot a laser in some direction. We just say we're going to assume the laser always goes in a straight line. If we are just, you shoot a laser across your backyard or something, you'll just see that this light will just go in a straight line. Okay, so the big idea of the standard theory of gravity, general relativity, is that actually the beam won't always go in a straight line, and doesn't always go in a straight line because the structure of space is curved. So, for example, one of the rules will be that the light always goes on the shortest path it can. Given 2 points, it's going from here to there. The light will always take the path that is shortest to get from one point to another. What is the shortest path? Well, the shortest path depends on what space you're in. So, for example, on the surface of the Earth, the shortest path between 2 points is this great circle path. That is, on the surface of the Earth, if you looked at it from outside the Earth, you would see that the path is curved because it's following the surface of the Earth. And if you imagine that you're on a surface and the surface has a certain shape, you can see that the shortest path between 2 points, when you're keeping on that surface, won't be something that is a straight line when viewed from the outside. And so the basic point in Einstein's theory of gravity is that, which our new theory of fundamental physics nicely reproduces, the basic point there is that when there is a mass, when there's mass in the universe, it causes the structure of space to be deformed. It causes curvature in space, and that curvature in space will deflect the paths, deflect the shortest paths. And so what happens is, when you have a massive object, the space is curved, the shortest path is no longer a straight line. It's instead something that's deflected towards the mass, and it's deflected in just the way that corresponds to the deflection due to gravity of that particular thing. So the basic point is, when there is mass, so-called GD6 shortest paths are attracted towards the mass. It's basically the same thing as I was talking about earlier in terms of things fall towards massive objects. Gravity pulls things in. You see that in the convergence of these GD6. Well, what happens is, inside, one of the sort of defining characteristics of black holes is they produce this convergence of paths. So in other words, all these things, even though they're coming from all these different angles and moving in all these different ways, they'll all converge to a point. And one of the things that I was going to explain what the singularity in space-time is about. Oh boy, let me see how to best talk about that. Essentially, what happens at the singularity is that the curvature of space becomes infinite. And so you can measure the curvature of space by asking, for example, if you were to have an object there, how would if you look at these GD6, these paths, you can ask questions about how much deformation in that path will there be. And in the sense, at the center of a black hole, there's infinite deformation in the path. So what actually happens is, and again, it's a little complicated, but what basically happens is that the end result is that time stops. So these paths are going along, they're converging. Eventually they get to the point where they've completely converged and the paths have no place to go. And so in that sense, these paths they're sort of progressing with time, but at some point they've converged to the point where they don't move through time. They are just stuck. Time stops. And so the way that will, if you were just sort of falling into that point, then you're thinking, oh, time is passing more slowly. And then you get to that center point and you can no longer, you are completely stuck. It's like if you were a computer that was running, the computer's clock would stop. The computer there would be no further instructions executed. The computer wouldn't know that anything had happened to it because it wouldn't know anything. It's just stuck. It's just stopped. And so what happens is that at the center of a black hole, well, at least the simplest kind of black hole, time just stops. All of these different paths of what happens to anything that's sort of falling into the black hole, they just get to the point where nothing further will happen with them because time is effectively stopped. Now, that's true with the simplest kind of black holes, so-called Schwarzschild black holes, which are non-rotating black holes. There are other black holes that are rotating, so-called Kerr black holes, and the situation with them is considerably more complicated. And they have a different kind of, the thing I've just described is called a space-like singularity. It's a place where basically time ends. There is, what can happen in other cases is there are places where space ends, where all of space is crushed into a single, there's just this sort of single point in space, and time progresses, but nothing can, there's no possibility of any extension in space. So now the question would be, if, so when time ends, if you ask the question, does everything that kind of goes into the sinkhole of a black hole, does it all end up in the same place? Does it all go to the giant sewer of the universe or something? The answer is, well, not in a Schwarzschild black hole, because time just stops. It doesn't go anywhere. It's just like, it's frozen. Okay, in the case of a Kerr black hole, these rotating black holes, it's a more complicated story. And let me think about that for a second. Yes. Okay, so in the traditional theory of gravity, every black hole that forms is its own thing. There's no connection between any two of them. And so that means that whatever is formed there, there's no possibility of some kind of weird wormhole in the structure of space-time that connects this black hole to this other black hole over here. That simply can't form in the way that, I mean, in formal terms, there are these Hawking-Penrose singularity theorems that tell you things about how singularities are inevitably form in the structure of space-time when there are these massive objects that collapse. And in the structure of those theorems, I think it has to be the case that every black hole is its own island, so to speak, that there's no possibility of a connection between these different black holes. That's true for the traditional theory of gravity. In our theory of the structure of space, which kind of goes into more detail and kind of tells you what space is made of, rather than just telling you kind of the characteristics of space as we observe it. In our models, it is more possible to have connections between different, in the usual model, the main issue is that you can't change the topology of space. So topology is something like, you have a sphere, it's got no holes in it, you've got a donut, it's got a big hole in the middle. You can't continuously deform a sphere to make it into a donut. There's some moment at which the hole first forms, and that's sort of a discontinuous thing that's happening. And in the universe, you can't kind of go from being something that sort of doesn't have a hole in it to something that does. In the standard theory of gravity, that's just impossible, just can't happen. In our theory, that actually can happen, at least at very small scales. And so it's more possible that you could conceivably have a connection between two black holes. It will not be a natural thing to form because most black holes are just forming as a result of a star collapsing, and so that won't happen. There can be a slightly bizarre phenomenon, which is a connection between a black hole and a white hole, and that will get us into a whole another can of worms. White holes presumably can't actually exist in our universe. Presumably they're infinitely unstable. And anytime a white hole, which is kind of a thing which spews everything out, anytime that's happening, there will be an instability which will cause it to no longer do that and sort of break into a bunch of black holes and so on. The one exception to that is, in a sense, the beginning of our universe, the Big Bang at the beginning of our universe, is a little bit like a white hole. But in general, things, it goes the other way, that things always sort of converge, that mass always makes things converge. Well, let's see, maybe one or two more questions. Oh, there's a question from Stenio. Do black holes rotate? Can they distort the space-time around them? Yeah, well, so any massive object is distorting space-time around it. And that's because the presence of a gravitational field is, in Einstein's theory of gravity, equivalent to a distortion of space-time. Black holes can rotate. Typically, a black hole, you might say, you look at a star has all kinds of protuberances and, it's sending out all these giant jets into space and so on. A black hole, the actual part of it that's associated with its event horizon is very perfect. it's a very kind of smooth event horizon. There can be all kinds of things that happen outside the event horizon, but the actual event horizon is something very smooth. And the only characteristics that one can typically tell from the gravity outside of the event horizon are the total mass of the black hole and the angular momentum, the rate at which the black hole is rotating. You can also tell things like electric charge and so on. But so yes, there are rotating black holes. In fact, most black holes rotate. The thing that is interesting about black hole rotation is there's a limit to the rate of rotation. Given a particular mass of black hole, there's an upper limit to the rate at which the black hole can rotate while not changing the structure of space-time a great deal around the black hole. One of the things that happens is a phenomenon called frame dragging, which is when you're close to the black hole, it's as if light that gets close to the black hole is kind of dragged around with the black hole. It's a little bit like, it's almost as if there's sort of it's almost as if there's the light near the black hole is made to be, it's almost like a friction between what's happening and the rotation of the black hole, and it causes the direction of light to be turned so that it tends to be dragged along with the rotation of the black hole. Okay, that's all well and good until you reach the critical angular momentum, the critical spin of the black hole, at which point what happens is, gets very weird, the event horizon. So normally in a black hole, there's this event horizon. Things can go into the event horizon. They cannot escape from the event horizon. At the center of the black hole, there is the singularity in space-time, this place where the curvature of space goes to infinity, this place where, for example, time stops or space stops or some other pathology happens. But that place where time stops, for example, is forever hidden from the outside world by the presence of the event horizon. So if you're going to say, I want to do this TV special about what happens at the center of the black hole, you'll never succeed, because once you've fallen in through the event horizon of the black hole, you can never send a signal back out to tell the world what you see at the center of the black hole. That's not true for black holes that rotate sufficiently fast. If the angular momentum in some units is bigger than the mass, if they're spinning too rapidly, then it would be the case that there isn't an event horizon, at least it has a very different structure. You can actually, there's a naked singularity, a place where there's actually the singularity at the center of the black hole can actually sort of communicate out to the outside world. People believed for a long time that black holes could never form where there were naked singularities. And that it was always the case that somehow when you have actual matter, that somehow it would always be somehow unstable, and somehow the black hole would eject material and no longer be going at the same angular momentum and so on, and that it somehow wouldn't ever be able to achieve that critical angular momentum. It turns out when you look at black holes that we actually observe, that there are a bunch of black holes that are very close to the critical angular momentum, but none that we've observed that have larger angular momentum. So it does seem to be the case that there's this upper limit on the rate of spinning of a black hole that is produced by some kind of instability. But people have believed that there was simply no way to get a naked singularity, no way to construct it. Then it was found, I don't know, maybe 10 years ago or so now, that by a very elaborate way of imagining, sort of adding matter in just the right way, you can actually sort of navigate things to the point where you have a very weak, but nevertheless non-zero singularity that is in principle accessible to the outside world. And actually we were about to start looking at how this works in the context of our models, because I think it's going to be a lot clearer there, exactly what's needed. My guess is that the sort of what you need to be able to maintain a singularity while not filming an event horizon around it is something that is a very complicated sort of put up job. It's the same kind of thing if you have molecules of gas in a room, if you could have this sort of microscopic device that every time it sees a molecule going this way, it bats it off to go in a different direction, and so on. If you had that microscopic device, eventually you could push all the gas into the room to one side, and leave a vacuum on the other side. But that's extremely hard to do because you'd have to have this little microscopic thing that's looking at every single gas molecule and figuring out exactly what to do. My guess is it's the same kind of thing that's needed to achieve this kind of arrangement of matter that will produce a naked singularity that does not have an event horizon around it. All right, I should wrap up in just a moment here. Let's see if there's anything that I think I can do I'll try one more. Boy, there's several interesting ones here, many interesting ones here. Okay, there's one from Good Lens here. What is the reason for the distribution of matter and antimatter throughout the universe? Why is there less antimatter? Okay, so first point is matter, protons, electrons, those kinds of things. One of the things that's a very fundamental piece of the quantum theory, of quantum field theory, sort of fundamental piece of particle physics, is to every particle, there's a corresponding antiparticle. Sometimes the antiparticle is the same as the particle itself, like it is for a photon, but usually, like with an electron, it has negative charge. There's also a positron with positive charge. There's the antiparticle of the electron. Proton, there are antiprotons, and so on. And so for every particle, there is an anti-version of it. And those anti-versions, things like their electric charge is the negative of the particle itself. The only thing that doesn't get negated is its mass. Its mass is still positive. That's an interesting thing that actually in our fundamental theory of physics, we actually understand why it happens that way. It's been much less clear why that happens, but we sort of understand why that happens. But so antimatter, positive mass, negative charge. When matter and antimatter meet, they tend to annihilate each other. So for example, an electron and a positron, if they meet up, they will eventually annihilate and turn into 2 or 3 photons. They will the energy that's associated with their mass will turn into, in that case, the photons have 0 mass, so it turns into sort of pure energy of the photons. Okay, so one of the things when I was younger we didn't know is whether a next door galaxy in our universe was made of antimatter. It could have been the case. It would seem very nice and symmetrical if, like, okay, our galaxy is made of matter, but the next door galaxy might be made of antimatter. And there might be a random distribution of matter and antimatter galaxies around the universe. Well, we probably know that that's not the case. We have increasing evidence that's not the case, because essentially, if there was matter in one galaxy and antimatter in the other galaxy, there would be a small trace of, for example, if 2 galaxies happen to collide, giant explosion as the matter and antimatter in the galaxy and the anti-galaxy annihilated each other. And we don't see things like that. So we kind of think that all the galaxies in the universe are made of matter. So that raises the question, how come, if that's the case, that means there's lots more matter in the universe than antimatter? How could that be? Why would the universe be asymmetric in that sense? Well, I actually worked on this problem about 40 years ago now, and we don't completely know the answer. There is at least a hypothesis, but it isn't a very good hypothesis yet. It matters to the hypothesis that, so roughly what happens, in the sufficiently early universe, if things are sufficiently hot, if there's sufficiently much energy being sort of pumped around, you make matter, antimatter, you make particle, antiparticle pairs. If you just put energy in, just like when electron and positron meet, they turn into sort of pure energy of photons. Similarly, if the photons have enough energy and you just sort of collide photons together, they'll make an electron-positron pair. And so in the early universe, when the universe was very young and very hot, the pure energy associated with that heat would have produced particle-antiparticle pairs. Actually, in the sufficiently early universe, it would produce antiparticle pairs for all possible kinds of particles, however massive they are. So there'd be top quark, anti-top quark pairs. There'd be proton, antiproton pairs, all sorts of things, more like quark, anti-quark pairs. But there'd be all these different kinds of particle, antiparticle pairs. So just generating particles and antiparticles from pure heat, so to speak, you get an equal number of particles and antiparticles. So how do you end up with more particles than antiparticles, more matter than antimatter? Tricky business. Okay, so the theory is, this is complicated. Okay, so the theory relies on certain things that have not been seen. So it is believed that protons seem to be stable. Protons are made from quarks and so on. It seems like protons never decay. But there's some decent reason to believe that if you were to wait sufficiently long, we know it's more than 10 to the 31 years, then you would see protons tending to decay. If you were, the lifetime of a proton, will decay at some very, 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 very slow rate. And a proton will decay into a positron and photons, neutrinos, things like that. That violates a bunch of sort of conservation laws that we think are true in physics, but at some very, very slow rate, those will get violated, we think. Never been observed, so we don't know that for sure. In the sufficiently early universe, that phenomenon would lead to, in this kind of, when you make things hot enough, you put enough energy in, that phenomenon will happen much more often than, actually, no, that's not the main point. The main point is, that phenomenon is associated with particles that have very short lifetimes, but which are doing things that will be like, it can sort of produce a proton from nothing, so to speak. But it happens, it's a particle that has very high mass, very short lifetime, can be produced in the very early universe, but wouldn't ever be produced subsequently, except in some kind of virtual way as a result of as part of the proton decay process. So in any case, the thing that happens, okay, in the sufficiently early universe, this phenomenon, these particles that we've never observed might be produced. We've never even observed their effects. For those who are paying attention to these things, the particles were believed to maybe have a mass of about 10 to the 15 times the mass of the proton. At least when I was working on these things, that's 40 years ago, and so it might have changed since. We used to call these particles with the very convenient letter capital X, but I don't know whether they've been renamed since then. But in any case, these particles, which we don't know exist, they would be produced in the very early universe. And the tricky thing is that, okay, this requires one more step, and then we'll, okay. When particles and antiparticles have the feature that their mass is always the same, their lifetime is also the same. If you have a decaying, let's say you have, I don't know, a neutron, which happens to, when it's isolated on its own, it decays at a certain rate. An antineutron decays at the same total rate. And that is a consequence of a thing called CPT invariance, which is a very fundamental consequence of the mathematical structure of quantum field theory. It turns out that the one thing that can be different is when a particle can decay in many different ways. So it could decay into this, or it could decay into that. The so-called partial rates of different decays can be different between particles and antiparticles. That is, the total lifetime, the total rate of the particle decaying is always the same, but the partial rates can be different. The partial rates are not forced to be the same by this fundamental feature of the mathematical structure of quantum field theory. And so the belief is that these weird particles, these X particles in the very early universe, had different decay rates to what now count as matter and what now count as antimatter. And as a result of that, those things will have produced, those particles will be produced in the very early universe. Their decay will be a little bit more preferentially to matter than to antimatter, only by about 1 part in 1 part in a billion, because that's actually the roughly in the universe. We know that if you just look at sort of all stuff in the universe, it's mostly photons and things like that. And there's only a small fraction of it that's things like quarks and electrons and so on. It's about 1 billionth of the universe isn't just photons. 1 billionth of the universe has this asymmetry between matter and antimatter. So that small asymmetry is associated, we think, with the difference in the rates of these particles produced in the early universe decaying into one thing as compared to the other. And the interaction of that with things to do with the expansion of the universe produces this long-term effect of there's just a little bit more matter than antimatter. And as the universe kind of cooled down, lots of matter-antimatter annihilation would have happened, but there'd be a little residue, 1 part in a billion, left over that is matter and not antimatter. And that's supposedly where we all come from. This is not a completely satisfactory theory. There are aspects of this where we just don't know whether that's really the way it works. And there are phenomena in there that have never been observed and that we think should be observable at some point if this theory is right. But that's the main prevailing theory for why there's more matter than antimatter in the universe. It's a sort of it's almost a footnote type theory. It's a weird little minor mismatch between the rates of decay into this thing versus that thing, and that leads to everything we know, which is sort of a curious feature of often the way that physics works. It's everything we care about is in a footnote, so to speak. And this is one of those cases. All right, I should wrap up for now here, and lots of interesting questions, which we can continue on next week. And I think next week is a holiday in the US, but we plan to do this anyway on that day. So thanks for joining us. I think I have to go do some work for my day job, and actually there'll be another live stream about completely different kinds of things with software design in just a few minutes here. So thanks for joining me. Bye.